Hello, this is Sixlo. If you're not in the right place, this is the time to leave. So before we start, I'd like to ask for a minute taker. We have a Jabber scribe already. Thank you, Rahul, wherever you are. Hopefully you're there out somewhere. But we do need a minute taker. Is there anybody who can take the minutes? And again, what we need is not detailed notes. What we need are just the action items. That's more than enough. So anybody can volunteer for that? Crickets? Any takers or no takers? Anybody? Really just action items, and I'll let you know when you need to take down anything. We'll let you know, hey, please take down this action item. This is what you note. It'll be easy. Charlie, thank you. Okay, so we're in Sixlo. Chairs are Shamita Chakrabarti, who could not be here with us today, and myself, I'm Gabriel Montenegro. We have our responsible AD. So there's Krishnan here with us. The note well, I assume you have seen it. If you haven't, maybe you should step out. This is important stuff. Make sure you know it. That's all I'm going to say about it. I assume you already know this. The agenda for today, we have some updates from the chairs, and we're going to have a series of updates from Pascal on the Sixlo ND document, basically on the ISG review. Then we're going to have updates on APND document, on the fragment forwarding document as well, fragment recovery from Pascal Tibet. And finally, also from Pascal, backbone router preparing for working with Blast Call. We're going to have then AD review comments, or looking at those for the NFC document. Similarly, working with Blast Call comments for the packet delivery deadline by Charlie. Then we're going to have an update on the PLC document. And finally, a performance report, some very interesting results from on the fragment forwarding drafts by Rahul. And to finish it off, we have Carles with an update on the BLE mesh. So there's some good news in the BLE mesh implementation front. The draft status, we have 6775 update, which is really, really close, and we'll hear more about that. And backbone router is getting ready for working with less call. APND is in progress. NFC is progressing. It was submitted to ISG. We have some AD review stuff to look over. Updates, as we said, on BLE mesh. The use cases document just issued working group last call, so that'll be on for another 2 weeks. This is the applicability document or use cases, as you may have known it. Please send your comments on that document, even if it's just to say it looks good, even if it's not detailed. So please do that, and that will run for 2 weeks. And finally, the deadline time document has been submitted for ISG review. We'll see some comments now. Suresh, is there anything?
Yeah, so the NFC and deadline time, like I didn't want to start an IETF last call during the IETF. So like the next week, I'm going to start the IETF last call for those.
Okay, thanks for that. Okay. On the fragmentation side of things, the design team was concluded some time ago, and now we're just having the 2 resultant documents progressing as usual. We have the minimal fragment and the fragment recovery, and we'll see some update on that today. And finally, and I believe Suresh already just sent an email to the mailing list, but both Samita and myself will be stepping down. And after this IETF, I may be even replaceable before the next IETF, Samita, I think for sure. So Suresh might have some words of wisdom here on how to handle the overlap.
Yeah, thank you very much, Gabe and Samita, like for all you've done. Like I really enjoyed working with you on this, and I hope you can continue to work here. And I really appreciate all the work you've done here. And personally, I want to start bringing in at least another chair in very soon, so there'll be a transition. And I don't mind going with 3 chairs for a bit, and then like eventually like transition like you or Samita out, right? Like, but so I don't mind putting as many chairs as needed to make sure this happens. And if anybody's interested, come talk to me, and I can brief you on what's required, like what is the status of the documents and everything. So it shouldn't be like too time consuming unless the work starts picking up again. So right now, like it's kind of manageable at this point, but like there's like bursts of work here. So like sometimes you might get like really overwhelmed by it. So just come talk to me.
Okay. Thank you. Yeah, and thank you. Really enjoyed working with you. So I guess we're ready for Pascal. There you go. Is Pascal in? Oh, okay. Guess we'll have to. Get out of this thing. So let's see. This one is also Pascal. No, that's it. Maybe we'll go to the next presentation. Yong Huang.
Oh.
Here it is. Yep. He's on his way right now? Why don't we go and finish through, and then we'll go back to Pascal. Yeah.
Should I go first? Thank you. Hello, my name is Yongwan Choi from H3, Korea. Actually, I've got the review, AD review from the internet and IoT. I've got a good comment from them, so I fully appreciate them. Actually, this is the Can we make this
Working correctly?
Yeah.
Hey, you want?
Okay, yeah.
Suresh Krishnan, so just had a comment. You said 11 and 12, so are you planning to publish at 12 soon?
Actually, I produced the 11 and 12, but the 11 is published, the 12 is the submission tool was not open, so I will submit the 12 also
Okay.
after this
Okay,
meeting.
so you want me to process 12 instead of 11, right? Because I was going to start a last call on 11, so you want me to wait till 12 hits, right? So
Yeah.
the tool is open now.
Yeah,
You can submit it.
okay, yeah,
Perfect.
yeah,
Thanks.
I will. Thank you. This is a quick introduction to the NFC every time I show you. This history, this status of this one, actually, we've got the revision number 10 from the new Shepherd Samita reviews, and I just produced and reflect all the comments from her. And after that, this time, I produced the 11 and 12, but 12 is not submitted, but after this meeting, I will submit this tool is open. Actually, the first one is the AD review from the internet. The review is Shang Jiang. Actually, he gave me just short comment, just the review result related to need. The comment was the reference is missing in the document, so I just put the section number 1 in about the anyway, about the reference in the section 1, the ECMO to 340 there in the red line. And next one is the IoT AD review from the Brian Haberman. Actually, the review result on the right track. There are a lot of the good comment. I just reflect all the comment, the 11 and the 12. And then the Brian showed me, he gave me that the message every change is the okay for him. The first one is the section 3.4. Actually, that was about the use of MIUX. Actually, in this document, the MIUX is must. I have a must be used, but I just put the keyword in the document, just change it, the keyword to should to the must. And the next one is the section 8.8. This is the kind of, in case of the lack of the MIUX, this is the MTU extension. So just I give the scenario, then the red box, if the NFC device does not support extension, the IPO of NFC use FR with default MIU as defined at RFC 4944. And next one is the section 4.3. This is about to increase the randomness of the generate IID. Actually, the network ID in the function is from the RFC the 7136 36. Actually, this network ID is the parameter is optional. So I just mentioned about this network ID in the red box like this. The function can provide secured and stable IID from NFC enabled device. In addition, an optional parameter network ID may be used to increase the randomness of the generate ID like this. And next one is section 4.5. This is about the explanation, the 6LR and 6LBR behavior of NFC device. Actually, section 4.5 just mentioned about the details of the behavior of LN, but he want me to put the behavior of the 6LR and LBR when the NFC device becomes the 6LR and LBR. So I just put the last bullet there. When the NFC device becomes the 6LR and 6 or 6LBR, the NFC device must follow the section 6 and 7 of RFC 6775. And this one is the last one. Actually, this is the scenario. There's no, he said to me, there's no any technical explanation about these two, the connectivity. So I just put two LED box there. Just first one is about the NFC-enabled device connected to internet scenario and topology. Just put there. I just mentioned about something technical. For example, the address collision or something like that. And next one is the isolated NFC device network. This is also I just put the technical there. That's all. Thank you. Any comments? Thank you. Thanks so much.
Thank you. Okay, thank you, Johan. Pascal.
So I'm Pascal Thubert, and we'll talk about a series of 3 drafts, which are working documents and work together. So these are the RFC 6775 extension series. And there's not 4 pages. There's a button you can press. Maybe this one here, so you get 4 pages.
I can press that one.
Okay. Thanks. So basically, we for a long time we had a prime statement document, and we turned that into 3 particular documents. And the goal is to extend what we could do with 6775, so that we can inject an unaware leaf into a routing protocol like Ripple or Backbone Router, which is a proxy ND, and make it SAVI compliant by preventing some address stealing and activity from an address which is not owned by the device. So the series of 3 drafts. The first one is RFC 6775 update. APND is the address protection draft for doing the SAVI, and Backbone Router is this proxy operation for IPv6 ND. So the news on the RFC 6775 update. So the draft does what we can see here. 6LoWPAN node discovers a 6LR through an RS array multicast, which is inherited for 6775. We have added the 6CIO to provide the capabilities of the node. Then we basically modified the way we build the NS with the extended arrow option, so that now we advertise the registered address in the target as opposed to the source on the packet. That's a big change. The other big change is that we have extended the size of the unique ID, so we can make it a crypto token of a larger size. And if the registration is complete, works, and possibly proxied on the backbone with the 6BBR Backbone Router, then the DNA goes back to the device. On the way, we have extended the DARDAC message so as to carry this bigger rover field, which is this extension of the unique ID. So this is the core of 6775 update. And the news is we've gone through the INS steps, so we're happy with INR. We've disambiguated the code with the RFC editor, so now the text with the RFC editor. So now we are in the RFC editor state for text cleanup, and we're waiting for the OAuth 48, which is hopefully coming soon, meaning that we'll have an RFC number hopefully before Christmas. If we behave. But we did one pass with the RFC editor already, so we behaved so far. Yeah. So that's it. The 2 other drafts are very active. The first one is address protection. So like I said, this one does 2 important things. The first thing is you're free to form an address. Any address doesn't have to be looking like a CGI. But since you have this registration mechanism, you register it with a crypto token, which ensures that nobody else can later claim an address that you formed. So the address is yours. as long as you maintain the registration active, nobody can come and claim that same address over 6LoWPAN-ND. The second thing is you need to declare your address to the 6LR. If you start using an address that you did not declare and validate with the 6LR, then the 6LR may actually destroy your packets to ensure that you're not issuing traffic on behalf of somebody else and attacking that guy by faking traffic. So the flow is like this. You send the NS with this new field called rover, which extends the unique ID, and now it's a cryptographic token. You can see that as if it was a public key. It's a hash of it, but it's kind of a public key. And if the 6LR doesn't have a registration for you or doesn't trust that you own this crypto token, then it can challenge you with a nonce. Classical challenge based on the private key and this nonce and the nonce that you also form. So the nonce on the NA, the nonce on the NS now are different. We have two nonces. We can actually, the 6LN will sign this whole thing based on nonce and the number of fields that we put in this SIPO option. And the signature goes into this NDP SO, which is the signature of all this, signed by the private key. Meaning that only the owner of the public key, which was used to build this crypto ID, can actually send this NS with the nonce, all signed with the private key. With this, you prove ownership of the crypto token. If the first registration ever for this address was done with that crypto token, it proves that it was you, the owner of this address. So the 6LR is happy with that, can recompute exactly based on the SIPO, it can recompute that this is actually what was used to sign this NDPSO and validates the NARO. From there, you register with that 6LR. So you can register with multiple 6LRs. And the first time you register, well, when you register to a 6LR, it will go to a 6LBR, validate that the registration already exists at the 6LBR. If it does, then it has to be the same ERO. Now the 6LBR doesn't validate the crypto token, only the 6LR does. So if we are in a mesh case, which is not a Wi-Fi case, but a mesh case, the 6LR can be separated from the 6LBR. The validation is done by the 6LR, not the 6LBR. So there needs to be a trust between those two. If they are the same box like a Wi-Fi AP, then obviously this problem does not exist. So recent changes is we finally got René Strick, the expert on security, to join us as a contributed author. And based on his help, we actually changed a few things. So one thing we rolled back is the SHA-256. We had this trick where we could use SHA-256 as opposed to SHA-512 for Edwards curves. And that's actually not compliant with RFC 8032 or something, so which mandates 512. So we had to go write an RFC on the security area to just define how Edwards curve at DSA would work with SHA-256. So we said, okay, too bad, let's use 512, which means that if you have an implementation that uses both the default NIST curve and the additional DSA curves, you will need to implement two different hash functions, one 256 and one 512. That's live. So these are the biggest change. So now we are kind of confident that we have the security level we wanted in this draft. So it's going to be very close to last call time. The recent change, not this one, it was done before, but basically as opposed to CGI, which is used in SAND, here we can have large token. CGI has this limitation that they have to embed the security token inside the IPv6 address because they don't have this registry up there where you can have both informations like we do. So they had to encode the security token into the address, making it 64 bits max. And so it was kind of easy to attack unless they did those special measures with all those bits that have been computed to 0, which makes it very intensive on the CPU to build. And so it's really something that was not compatible with IoT devices. We can't use a CPU-intensive method to build your token. So we ended up in the other way by saying, hey, we can make it bigger. So that's why now we can have it to 256 or 512 if we like. So we can have a large token, which avoids the CPU intensive methods that you can find in sound. So I already mentioned that the 6LR and the 6LBR, if they are separated, since the 6LR is the only one doing the validation, the 6LBR must trust that the 6LR is doing the right thing. So we still have this possibility that a rogue 6LR could inject addresses on behalf of a non-existent 6LN. So there needs to be something which is outside of this protocol to establish a strong trust between the 6LR and 6LBR. So if we don't have this trust, then there could be a need for doing the same kind of challenge all the way from the 6LBR. So it would really validate that whatever the 6LR says is actually true. Should it be done in this document? We don't think so. Should it be done in REPL? If you have REPL on the way, well, I do think so. So I propose that to roll this morning. If you have a REPL network there, could we cascade the trust chain all the way to the 6LN using a method that uses the rover? And probably I will propose that to roll soon. If the 6LBR is the same as the raw root, then that will give you the same property as if the 6LBR was challenging anyway. And that's what I also mean by, can the crypto ID be used by routing protocol? Basically, this method of challenge that we have could be recursive through REPL, in which case all the REPL routers would actually validate that what is advertised in REPL is actually an existing node at the edge of the network. So if you have any comment on that, propagating this trust all the way through REPL, well, this is welcome here or in ROLL. Now, we allow for a rover field that is more than 64 bits. Like I said, we have to get a good degree of security. Now, should we actually have stronger words for this? Kind of recommend not to be as small as 64. Again, if you have a feeling about this, it's a good time to go to the mic and say, oops, don't use 64, use larger. Second question to the group, and please come to the mic. If you think that it's really too costly to have to implement both SHA-256 and SHA-512 on a single device, and you think that you need to support both curves, come to us and go fight that fight at the security area to make an update of 8032 to support SHA-256 as well. I thought it could be trivial, and Mohit told me, well, it's not that trivial. So that's why we don't have it. And if you have anything above and beyond that you think is missing in this draft, it's good time for us to know before we ask for our last call.
Carsten Bormann, of course, I want to use SHA-3.
Okay. Do you have an RFC which says how to be able to use a certain curve with a certain SHA? Because I understand from Mohit, who is the expert, and with René, that each time you want to use a different SHA with a different curve, you need an RFC which puts those two together. So if you have an RFC that actually builds that nicely, right now we just have one optional crypto. We could have a second optional crypto very easily. For us, it's just to mention, if you have this bit on, it means that RFC. As long as it is a change like this, it's a good time for doing it.
Yeah, all I wanted to say is, how do we evolve this?
How do we evolve? Oh, well, we have bits, right? So we have basically only one mandated. It's NIST with 256 SHA. So this one is mandated, and all the others so we have some bits to have more, and we have defined only one value, which is the 512 with Edwards curve. And now if we have more RFCs with more bits, with setting the other bits, you can have more curves. It's just that right now there was nobody expressing the need for a third curve or a different SHA or whatever. So the bit is both a hash plus a curve, right? It's both the crypto and the hashing. And yes, we have more bits free. Anything else?
I have a question. Could you put back the slide that shows the 6LN and 6LR, that? So just requires all the 6LRs to have all the crypto information for all the 6LNs, isn't that?
Just during this flow, you don't need to maintain it. So basically, when you create the neighbor cache entry, whether it's cool to call it an NC or not, when you create this neighbor cache entry and you're programmed to validate the crypto IDs, you come back to the device and challenge him. That's when all this crypto ID parameter option comes into play, which lists all the parameters that are used to build the signature, which is in the NDPSO. So those parameters include a nonce, which is coming from the device, the nonce that was coming from the 6LR, and I don't remember what, but a number of things. And this is all signed with the private key that was used to build this crypto ID. Well, that corresponds to the public key that was used to build the crypto ID, right? So you, with the public key, which is actually inside the SIPO, you actually validate that you can build this crypto ID. And then you validate the signature in the NDPSO that signs the SIPO. That's how you make the connection between this crypto ID and everything that is being claimed here, including the crypto ID, which is here, the things signed here, the nonce. So you have this tight chain of security.
So if I understand what you're saying, you don't have to pre-configure 6LR with all these 6LNs.
No. All the information, because a 6LN is free to form to any 6LN is free to attach to a 6LR. A 6LN is free to form any form of address. Privacy is recommended, but you can form any address. It's completely independent to the crypto ID, and none of that has to be pre-programmed into the 6LR. The only thing is the 6LR must have enough CPU to do all those computation, validation, and it needs to have enough neighbor cache entries. So it can also reject DNS if it cannot store the neighbor cache entry. But if it can't, then it just needs to have the CPU to validate the SIPO and the signature. And then it can forget all this, because once it has formed the neighbor cache entry, the only thing you need to keep is the crypto ID.
Okay.
And the 6LN that goes with it, right? The anchor, MAC address interface, the anchor, which is what goes naturally in the ND cache entry.
So I have a question / suggestion. This will get a sector review, of course, like any other draft, and we got Renee. That's great.
Yes, which helps.
Which helps a lot. But the fact is, this is a very, very crypto-intensive document. I was wondering if it wouldn't be a bad idea to just stand in SAG, for example, in the SAG meeting and present it, because they might have feedback that we haven't thought about. I mean, they're the experts in the security area, open group, or something like that.
So you asked me, I'm not sure I understand the question.
Suggestion is, would you consider presenting this in SAG to get feedback from the open area, security open?
I would be happy to, or maybe Mohit. Why not? I mean, Suresh.
Yeah, Suresh Krishnan. So one thing, Gabe, is right, like we can ask for an early sector review for that, right? And that kind of, instead of presenting, because they're going to say like, oh, what's this 6LoWPAN and 6Low and stuff like that. So I think it might be good to just push the early review button. So I can talk to the SecADs and you tell me whenever like it's ready to go, like, and I can push a button for early sec review.
What I'm hearing is it's almost ready for working with last call. Is that?
I mean, unless somebody comes up with a requirement, I mean, we're pretty much there.
So
Right?
it might be a good time to start pressing that button.
Okay, I'll do it. Like I can put in like an early sector review request. I can talk to Tero, like he must be here somewhere. So see if we can get it assigned soon. Okay, so.
We were shy before Rene could actually do his pass on this document. We were shy to present it to the SEC area, but now that Rene has helped us, he has squared the angles, and I'm pretty happy with it. And Mohit did a big pass on it as well. So
Okay, I'll get it done right away, and I'll talk to the SecADs to make sure that it gets seen, because it's going to get sec review anyway, right? Like when it goes to like IETF last call and before it hits the IESG. But if there's like something we can avoid like earlier, I don't mind doing that too.
Yeah, and my intuition is it's so crypto intensive that taking an extra precaution, like,
Exactly,
an early
yeah.
review.
I fully
Instead of
understand.
SAG, that's fine, early review.
Yeah, like
or
we have the
something
same.
extra.
we have the same in LWIG. We are doing some elliptic stuff. Like it's probably going to go through the same path. There's like and Rene is involved in that one too. Surprise, right? So, but yeah, so that's kind of the thing.
Yeah, a critical thing is it's by orders of magnitude less crypto intensive than CGA because you don't have to match those bits. Still, it's a public key, private key exchange. But the operation that we describe here is really, really classical, right? You get announced, you sign it with your private key. That's life as usual. So I don't expect much surprise. The one thing to remember is that the 6 LBR doesn't get to validate the 6LN, only the 6LR, because otherwise we would need a flow all the way from the 6 LBR. And we have not designed that flow. So we have that trust that is not specified in this document, whereby the 6LBR really trusts that the 6LR is not compromised, which is only a problem if you have a mesh. This is why I want to actually recursively close that gap using the routing protocol in between, all the way to the 6LBR. So I will have a proposal to Ripple to actually do that. So you will trust the DAOs as they flow. But I don't see, once we get that, the 6LBR will have the trust from Ripple. And part of what we do in Roll is actually to avoid having both 6LoWPAN and Roll do the same signaling. Like this guy keeps updating Roll that it's present. And you, at the same time, you should normally have to say to a 6LBR, I'm still there as well to refresh the lifetime, where we condense those two. And for the same reason, we would like to condense the security so that if the chain of trust is actually done within Ripple, we can go all the way to the 6LBR without having a L6LR to 6LBR communication doing the exact same thing.
My feeling about this is the document, what to think of these protocols and end-to-end solving the entire thing. This trust between 6LR and 6LBR is essential for this to work. If that's not encompassable or definable within this document, within 6LoW, maybe that means it should be in Roll. I mean, if Roll is the way to solve it.
Roll will need that element and it will build on it.
And if that's not the case, at least what this document should have, what are the requirements of the protocol that solves that 6LR to 6LBR? At least that should be here. Maybe it's already there, I don't remember. But such that those requirements in Roll, that would be one example. Here's how we solve those.
Oh, okay. So I don't think there is words to do exactly that, so we can add them. And your help will be appreciated. I think the words that we have in the security section is that we are creating a boundary of trust at the 6LR, meaning that we protect the Ripple network from the leaves which are not part of the Ripple network and not necessarily trusted. But we still expect that the Ripple network itself is kind of protected. This is true if you have like your keys and all, and there is no compromission, right? Because you have this, when you have this Ripple network like a CG Mesh or a YSAN network like for your electricity, then they will protect all the way to the meters. But if you decide to attach a washing machine to the meter using 6LoWPAN, you don't want the washing machine to inject anything in Roll, right, in Ripple. So that's when you want to establish this boundary of trust between the electrical network, which is all trusted, and those things which come from the outside, like your washing machine. So that's where this draft plays. But if you can imagine that an attacker would really attack your electrical meter and would be able to compromise it and inject things, if he was doing this, it's true today in the field, then he would be able to claim that his any meter or send any metering information or whatever else, which is why we want this zero trust model where every 6LoWPAN, every router would check that the 6LN is here. So Ripple would basically allow to go all the way down from this router there to the 6LR, and that's the 6LR to challenge with a nonce that comes from up there. And recursively, you could build this trust because each time you go and challenge all the way to the 6LN. We need to build that in Ripple, but we could mention it here. But right now, the assumption for this draft is, yes, we are just building this layer of this boundary for the Ripple network where we establish this trust. But we think that the whole Ripple network or whatever routing protocol you're using, because this is agnostic to Ripple, is trusted. So that's written in the security section that we need this trust inside the network. But we are not saying that we are willing to work in Roll to do it, because that's just willing. I don't know how far, I mean, you have to word that correctly. will be appreciated, because I don't know exactly how to word that we want to do something more. But it's certainly a tool that we need to go all the way inside REPL. We need to be able to challenge all the way to the leaf. And I'm saying REPL, but any routing protocol could do that. Okay, and so the news, yes, like I said, I think I'm through this. And the last of the three drafts is the backbone router. So this one, okay, remember the RFC 6775 is like a Wi-Fi association, right? The second draft is like making it secure so nobody can steal your Wi-Fi MAC address equivalent. So this MAC address belongs to this guy, it's there and nowhere else. The third thing that you need to have the equivalent of a layer 2 operation is the proxy operation between the Ethernet side, which is doing normal ND, and this registration. And so that's what the backbone router is. It's one of those quote-unquote routing protocols that can consume the 6LoWPAN registration and turn it into something else. So we already know REPL, which turns with the REPL unaware leaf, we turn the 6775 into a REPL packet, into a DAO. We have Rift, which turns that into a TIE. And now we have the backbone router, which turns that into a proxy ND operation. So the news on the backbone router is that Charlie actually joined. Thank you, Charlie, for joining. And already did a good cleanup work, just like he did for the RFC 6775 update, but this time way ahead of time compared to last time, which is also appreciated. For me, it's kind of complete, but I understand from Charlie that he wants to do more and that you think that it's not fully ready. And basically, you need to chime in to say exactly what you think here. So we don't know if you're ready, because I would think we are, but now I have a co-author who does not necessarily think he is. So. Okay. Well, can we still call? Last time we said we would call for our group. Last time you improved the doc by reshuffling it. You did not really change any semantics in there. It's just that editorially it's a lot more readable. If it was almost right for last call, I think we're still right for last call. So I thought that you thought differently. Now you're neutral. So I would say we're where we were last time, so ready for last call. Now, if during the last call, you can always comment again, right? It's not like, it's not. Okay, so if you want to go for last call for this one, I mean, it's been stable for, apart from the nice editorial things,
Okay.
It's been stable.
So the authors pretty much think it's ready for last call. Let me convene with Shamita and we'll decide within the next few days or so.
Very good.
Okay.
And you'll find in the slides the flows, which are how you do the proxy operation, blah, blah, blah. So, and that's it for me.
Thank you, Pascal.
Don't know what time.
Thanks. This one we did. Yeah, this we did. Deadline time. Is that you, Charlie?
Oh, yeah.
Yep. I'll make sure I take notes while you're up there.
It's likely to be a short presentation. So, hello, I'm Charlie Perkins, and I'm going to talk about the deadline draft. Overview basically is that this uses one of the routing header extension types to provide deadline information for packets that are to be transmitted over the network to the destination. And not only does it have the deadline time, but it optionally allows you to include the origination time, so you can better be able to take statistics on delays and so on. So this enables intermediate routing points to have delay-aware forwarding and scheduling decisions in particular, if the deadline's passed, it's a good idea to possibly drop the packet and just not waste any more bandwidth on it. So if you, since you are trying to make decisions based on particular deadline time, it does already essentially imply the requirement to have a time synchronized network. And since you already, oops, this thing is getting tired. Hold on a minute. How's that? It was drooping. It's been working too hard. Okay, now what do I do? Okay, so, well, since we already have to have the time synchronization, it also immediately allows us to handle different time zones based on the router's knowledge of the time zones that it's routing into. So the draft has been discussed many times during the ITF. We had a few revisions for the individual draft, and it was adopted as a working group document 3 IETFs ago. And then we had a revision based on a lot of editorial corrections and suggestions from the reviewers. And then recently there hasn't been very much done to it, and we'll keep looking at it. And I think it's pretty much ready for last call. We had good reviews from directorates and Georgios Papadopoulos, co-chair Shepherd review from Samita. Thank you for those reviews, very helpful. And here's the updates that have been made. We had in the document some description about the 6-low RHE, and we just replaced that by reference to the published document and put in a figure to illustrate the change to the origination time when you cross to a different time zone, because if you want to have an accurate view of the origination time, it really needs to be done in the time zone according to the time in the time zone where the the packet is traveling. We had used 6-TISH as an example, and it was intended to be an example, not a normative. In other words, you don't have to implement 6-TISH to have a conformant implementation of a deadline draft. And similarly, there was an example shown for how to do OAM, and that was draft that cited a draft that's done in another working group. And it's progressing nicely, but anyway, it's just an example. It's not normative on this draft. There was a question from one of the reviewers that when is the origination time? And so from the point of view of the application, what matters about the packet traveling over the network is how long it takes since the application essentially tried to transmit the packet or requested the packet to be transmitted. So I think it's logical to imagine that the origination time is as close as possible to that, which at the layer of processing for deadline draft would be when the packet is in queued for transmission. So that essentially made that very specific. And then we included, just mentioned a couple of other sources for why a packet might be delayed. And then there was some discussion about, well, we have this, if the packet really could supposed to be dropped, but if you set the D bit to be 0, then you can still forward it. Well, why would you want to do that? Well, you wouldn't want to forward it if for instance, if there was any congestion in the network or any reason to conserve power, or a lot of reasons. But if you have a reason, then it's not actually a protocol violation to forward the packet if the D bit is set to 0. And then finally, we just upgraded the bibliographic citations for the mesh and YSUN. So I think you've seen the packet format quite many times. Just to mention that the times are actually represented in somewhat of a compressed format that It shows the time units here. One of these 4 possibilities, or actually one of these 3 possibilities, and then the exponent to allow you to have a very wide range of possible deadline time specifications. And the same thing is true for both the origination time and the deadline time. Those two use the same scheme basically. So that allows compression of the numeric format. And that's about it. I'd be happy to answer questions. I don't think there's any remaining issues on the draft at all. And I guess we'd like to see it move forward.
Yeah, Suresh Krishnan. So I told Gabriel too, so the timing of the draft submission was October 15th. So it was kind of like difficult to do a last call around the IETF. So like when the IETF finishes, I'll start off the last call
Okay.
on this.
Any other questions? Well, thank you very much.
Okay. Next. PLC.
Hello, everyone. So currently we have arrived at the 5th version of this draft. So we have done some revisions based on the comments that we have received during the last IETF in Montreal and on the mailing list. So there was concern raised during the last IETF. It was about the privacy issue in the IPv6 address auto configuration for PLC devices. So in the last version, one of the options to configure the IPv6 address for PLC devices is by combining IP prefix and ID derived by the EUI addresses. But if we use such kind of address to communicate with the public network, there may be some privacy issues because it could be recognized what kind of device it is and who is its manufacturer and what kind of traffic it is. So in this version, we have added some limitation to such kind of addresses. The EUI derived IP address can only be used for link local purpose, and it should not be used for communication with the public network. So the second issue was raised on the mailing list. It is about the terminology. As you know, in this draft, we have covered 3 different PLC technologies. And in the last version, the terminology was not well aligned. So in different sections, we have been using the terminology from different PLC technologies together. So it may create some obstacles for readers to well understand the content. So in this version, we have cleared out this kind of situation and use well-aligned terminology in the whole draft. And a terminology mapping table is also built to facilitate the readers who are familiar with different PLC technologies. So the second issue was also raised on the mailing list. It is about the fragmentation. The last description about the fragmentation may make some readers confused because, in fact, PLC technologies have its own layer 2 fragmentation capabilities, which fragments the packet into different sizes according to the channel condition. But there's nothing related to what we do in the adaptation layer. Whether the fragmentation is required in the adaptation layer depends only on the MTU that layer 2 supports. So in this latest version, we have added some clarifications to to help people understand this situation. So we have done other modifications. It is based on comments on the mailing list, and hopefully it will help to make this draft more clear and more comprehensive. So for the next step, I think we would like to call for working group adoption, because currently, except the power grid related scenarios, more and more IP-based applications are communicating via PLC devices. It should be better to have a guideline for PLC IPv6 adaptation. So looking forward to your further comments. Questions? Thank you.
I'd like to get a sense of the room here. How many people have read this draft? About 3, 4, 5 or so. How many would be willing to comment on it and see it through if we were to adopt it? Okay, about the same number of people. How many would be interested in implementing it? I don't see any hands, but I do see at least some interest in commenting and seeing it go through. Not a lot, but okay. So I saw about 5, let's say 5 hands go up for some level of support, which did not include implementation, but yeah, showing some support. So let me take that. I'll consult with Samita, and then
Okay.
we'll come back on the working group call for adoption.
Okay. Thank you.
Yeah.
Thank you, guys.
Thank you. Okay. I think we're ready for, oh yeah, Rahul.
Hello everyone, I'm Rahul Jadhav. So the presentation is about the fragment forwarding performance. So there are 2 drafts that have been that have been added to 6LoWPAN Word documents, which is the fragment forwarding and the fragment recovery. So there is another competing work or the similar work that's happening in LWIG also. So we were highly excited about the prospect of using fragment forwarding because we had some specific use case. Basically, in our networks, for the authentication, the fragments are mostly fragmented. If the fragmentation forwarding can help us, it could essentially mean we could decrease the network convergence time. So that was our primary motivation. So briefly, let me just explain what the fragment forwarding is all about. So this is the traditional 64944 mechanism of per hop reassembly. You receive fragments, you reassemble at the next hop, and then you refragment and then send it upstream. Finally, it reaches the border router, and then it can decide again to fragment it or not to send it to the.
For mesh over.
Sorry.
For mesh over,
Yeah, for the mesh networks.
not for mesh under.
For the mesh over, yeah. So the important thing here is that all this is happening on top of mesh over or route over networks. In mesh under, this already happens the same way. Like you have a similar mechanism in mesh under already. It already does fragment forwarding, but I'll come to that point in the later slides. What happens there? So with regards to fragment forwarding, what we are trying to do is the fragment train is forwarded. There is no reassembly happening on the intermediate routers, and the fragments are forwarded as it is. There is a table that has to be maintained here, which contains information such as tag, sequence, IID, and the timer as well. Because at some point of time, if all the fragments do not arrive, the corresponding entry has to be removed. So there is a timer as well. So this is the state information that is involved. Here, the complete reassembly packet, so basically 1280 bytes of IPv6 MTU has to be stored here. So which is avoided in this case. So it is much more, so fragment forwarding is much more memory optimized. So our motivation, like I mentioned before, so when we started this experiment, we wanted to primarily check the latency and PDR implications of using fragment forwarding. We were less focused on the memory utilization. Actually, the memory utilization part was already covered by a yacht in the previous IETF 102, and it showed that memory utilization is good. The motivation for us was, again, as I mentioned, in case of EAP PANA, the header size is actually very bulky for EAP PANA, which causes fragmentation in 127 bytes MTU network. So we wanted to check whether fragment forwarding can actually improve the conditions there, which can directly result in improving the network convergence time. We also wanted to try for other bulk traffic such as meter readings, but turns out that we already use CoAP blockwise transfer for that. So it's not much of an issue. This is the test configuration we had. We used 802.15.4 in unslotted single channel 2.4 gigahertz mode of configuration. It had carrier sensing enabled, but 802.15.4 does not have RTS CTS, or at least we don't have it. I don't know whether anyone else supports RTS CTS here in 802.15.4. It would be very interesting for me to know. The L2 MTU is 127 bytes. The maximum MAC retries are 3. The network configuration, we had just 50 nodes. It was a great topology, and I mentioned the internode distance. We used ripple routing with MRHOF with ETX as the routing metric. Trickle parameters, MRHOF thresholds were all same across all the nodes and across all the experiments. The data transmission, so what we did was we had a 40 seconds interval for the data, and each data packet was 256, or each payload was 256 bytes for 40 seconds, which resulted in 3 fragments. For 80 seconds, it was 512, which resulted in 5 fragments, and for 160 seconds, it was 1 KB, resulting in 9 fragments. So what happened, what we are trying to check here is that if you increase the number of fragments for a particular payload, there would naturally be high probability, it would result in increased loss, because if any of the fragment gets dropped, the whole payload is lost. Yeah, Pascal?
Just asking, I think I know the answer, but just for the group, did you try sending 2 big packets in a row?
Yeah, so we have not tried that. We did, as per this data transmission policy, we don't send multiple payloads in a row. Yeah, so what we did was this. So basically what we did was 40-second interval. So the scenario that we simulated was you have big bulk data once in a while to be sent.
Just 1 packet?
Yeah, just 1 packet. Yeah, but across all the nodes sending it at regular intervals.
Because basically whatever we'll show here would show exactly the same way, but worse, if there were 2 packets in a row. But then it just would not be 2 fragments interfering, but all the fragments of 1 packet interfering with all the fragments of the next packet, which would make life an order of magnitude worse. Okay, so when I talked to the guys in our own mesh development team, and I told them, when you have the root having to send packets to multiple guys, just for the room, because you know already, I told them, don't send 2 packets in a row to the same next hops. If you have multiple packets that are to be sent from the root to a different next hop, shuffle them. So that you send 1 packet to this next hop and you can forward it at the same time you can start sending a packet to a different next hop. So they don't kind of collision at the first hop or something. So it's kind of a rule of thumb recommendation that is in that space.
But even that scenario, let's say, for example, we actually send up to a different parent. What's the guarantee that the other 2 parents, the 2 preferred parents are not directly in range of each other? I mean, that is still a possibility.
They
it does
will
not
interfere, but at least you will avoid the first effect, which is the next hop is forwarding the first packet as you're sending the second packet to him. He can't be listening to you if he's sending to the next hop.
Right.
So at least you avoid that first hop effect. As it goes, we are working in a YSAN environment, which has the channel hopping technology. So we don't really care about the next hop. The answer to your question is they will be operating on different channels because of the channel hopping.
Right.
So the real thing that concerned me was if I'm sending 2 packets in a row to the same guy, he will be transmitting the first packet and he cannot receive the second. I will transmit for nothing.
Yeah,
That's really what concerned me.
Yeah, thank you for this scenario. Actually, there are a lot of scenarios that we haven't really tested. It's not like this is a comprehensive performance report of all the scenarios and all the layer 2 mechanisms that can be, it's not. So basically this that's why I'm specifically showing this is the test configuration that we had. This is the data transmission scheme. Maybe it is not, it is skewed to a particular use case. It is skewed to a particular scenario. But yeah, that's how it is.
I love your work. It's an eye opener. Okay, so it's great. I love it. Now I would like to see more and more and more, because it's like you've seen a crime scene from an angle, and just by looking at it, you can't deduce who's guilty, right? You have to go around this crime scene, study it, and you will learn a lot more, and then you can draw conclusions. I think it's great work, and it's too early to draw much conclusion. Some of them, which we can draw, we kind of knew them before, so we are not surprised. Maybe it's worse than we thought intuitively, but it's not so surprising, right?
Right.
Okay.
Yeah. So yeah, it's not. So that this came as a big surprise to us as well. That's when we were not okay. Anyways, let's go to the data part and then we can have that discussion. So this is the packet delivery, the rates that we saw. So if you see the per hop reassembly, there's fragment forwarding with no pacing. Then we have fragment forwarding with pacing, 50 millisecond. I'll come to what pacing, what exactly pacing is in this context. So if you see, pretty much per hop reassembly is working out very well, except for that if you introduce pacing with fragment forwarding, it slightly improves, but statistically it's insignificant. So fragment forwarding with pacing, with a good amount of pacing, works as much as good as per hop reassembly. So this is the packet delivery rate, and you can see the packet delivery rate reduces drastically with this scenario, because there are more number of fragments for a particular payload than this and the other scenarios. What is pacing? What we added here, we had this discussion on the 6-flow design team, and Carsten and Pascal suggested about use of pacing. What it means is, on the sender side, we introduce a fixed delay before every fragment is sent in the 6-flow layer. So what happens is it increases the latency, right? It naturally increases the latency, but it also increases the overall packet delivery rate. That is what we saw in the previous slide. So, but here you can see what happens to the latency. So latency goes really, really bad for the fragment forwarding, even with pacing. But pacing does improve PDR. That means there is some L2 layer things that are happening here, which is coming into play. You can see here from the MAC transmit failures that there are clearly a lot of MAC failures that are happening when fragment forwarding is used. Yeah, Peter?
Peter van Stoock, small clarifying question.
Name, please.
Does the pacing allow the pacing between fragments of different streams, or just one packet with its fragments?
So every packet, every payload has this 9 fragments. Every fragment is been paced. So before sending a fragment, there's a delay of 50 milliseconds.
What is for interleaving? That's what
It's interleaving, yeah. It's interleaving, yeah. Essentially, it's interleaving. So you can see clearly from here that the MAC transmit failures is pretty high in case of fragment forwarding, and it becomes low if you introduce pacing. Now, this MAC transmit failures are complete failures. Even after 3 retries, the packet could not be sent. The data in the GitHub, it shows what happens on first retry. How many of the actual packets go through first retry, second retry, and third retry. So all this data is available on the GitHub. Observations: FF seem to be doing bad without pacing. Having said that, like I mentioned, it's for this particular L2 scenario. For a single channel hopping, anyways, I'll come to that in the next slide. If you add pacing, then latency is impacted negatively, naturally. Per hop reassembly seems to be doing better both in terms of PDR and latency, at least in this particular scenario. Basically, we were almost on the, we tried experimenting with this because we wanted to actually use it, deploy it in our scenario. But maybe because of these reasons, we could not go ahead and deploy it. Maybe if the L2 layer changes for us in the future, maybe we can consider it again. Or if there is any MAC interface which has advanced primitives such as RTS or CTS, it might be better to use. Fragment drops for us due to memory unavailability was very less. It was nil, almost negligible. Because if you see the kind of data transmission scheme that we had, you might say that it was skewed to our scenario. So we didn't have really any packet drops because of memory unavailability. And we used a grid topology. So there was not a single bottleneck node. So it was a grid topology. There was sufficient balancing. Traffic pattern was sparse. More fragments, it results in higher payload loss probability. Here, I feel maybe the fragment recovery mechanism might be of some help. Having said that, we have not really experimented with that. Yeah, Pascal?
Pascal Thubert again. You mentioned RTS, CTS. Since there is no master, it's very hard to do on a multi-hop because you don't know who would send the clear to sound. But from your own observations, it seems to me that your clear channel assessment is not optimized. Like, it's probable that two hops kind of send at the same time so they don't see each other. If there was some randomized time here when you start to send, even if you don't have a big delay, and if you had changed your threshold of sensitivity to the energy in the air, you did not detect well enough that there were those collisions. And that's about your tuning of your network, right? Sensitivity to energy detect and randomized time to forward so that they don't try at the very same time. And so one detects the other and there is no collision.
But at the same time, we had fragment for hop reassembly working in the same network with the same parameters. So what I'm trying to say is, these schemes will come into picture even for, and it will improve scenarios for fragment hop reassembly as well. So this is a generic thing that you mentioned, which will work even for fragment forwarding, even for per hop reassembly.
Yes, but the point is just try. We give you some we exchange, right? So we said, hey, you need this pacing thing. Well, you use the same value exactly at every hop. You did not randomize it at all. It seems to me that you kind of force those collisions by not playing any randomization game and not being very sensitive to energy detect. So if you do those two things, you instead of putting 50, you said a random number between 10 and 50, and then you say, either I lower my energy level because maybe you're crying out a lot too high, or you're not sensitive enough to the energy detect. By just tuning those things, I think you can dramatically change those numbers.
Yeah, so you're saying the pacing with some randomization between 50 millisecond or 25 millisecond to 100 milliseconds, something like that would have been that
10 to 50, yeah.
Yeah, 2050, okay.
And energy detect level, right?
Oh, yeah.
Detect multi-hop collisions. Now, you should not be having all those layer 2 primes that you observe today. I think you transmit at the very same time. You cannot detect it, all the possible things. So it's kind of a worst case scenario ever that you're building here.
But the same worst case scenario should apply for per hop reassembly as well. I mean, what I'm trying to say is,
if you send only one packet, I think you will go in hell with this. If you send more than one packet in a row, you will go in hell. It's because you send only one packet that it never interferes with the next packet. If it did, I think hell would break loose, but maybe not.
Yeah, so what I'm trying to say is here, all the nodes apart from the border router are sending to the border router. So there is a chance of other nodes. I mean, that is why we don't have 100% maybe PDR here.
Yeah.
But
depends on the load you have. But the premise with one thing like that, or two packets following one another, they are kind of synchronized loads. And if they cannot even detect the other because the transmission are synchronized, then you lose all the protections you have at layer 2. So you enter this situation.
Yeah, clearly we have a lot to check out. Definitely, yeah. So randomization is something that we thought about, but then it was not that trivial to implement. So we just gone ahead with the fixed delay. Yeah, but fixed delay it gave you a clear picture that actually pacing, if you do some sort of pacing, it will improve. And how exactly to do pacing, even if you have like 20 to 50 millisecond randomization, it might still induce latency.
You had to insert a very huge pacing because you had to maybe ensure that the packet went all the way through before you could the fragment before you could send the next one. But that's because your clear channel assessment didn't work at all. Otherwise, by having a small weight just to make sure they don't try to send at the same time and then detect the energy in the air would have done the job that you would want from RTS, CTS.
But okay.
Because so the short version is fragment forwarding increases the concurrency in your network. And if your network has trouble handling concurrency, then fragment forwarding is a bad idea.
Yeah.
But there may be other sources of concurrency, so you better make sure your network does handle concurrency.
Concurrency, yeah. Okay, so again, these inferences are drawn in the context that we were experimenting in. So FF performance is tied to L2. So L2 with RTS-CTS based CA mechanism, or not necessarily RTS-CTS. There are advanced collision avoidance scheme in, for example, like 802.11s. It has its own mesh collision avoidance scheme. So some of that scheme might actually benefit fragment forwarding. We have to remember one thing, that any mesh under protocol actually uses a stream train of if you generate a payload which is bigger than what MAC can handle, it is going to generate a train of fragments. So in that case, mesh under already has, if someone uses a mesh under routing protocol, then the fragmentation at IP layer is going to cause a train of fragments. So it is going to fall into the same problem statement as whatever we are discussing here. It works today, but having said that, for 802, I tried checking what 802.11s does, and it has this advanced mesh collision avoidance schemes, which which prevents such things from happening. So basically, the ball is in the lower layer, L2's layer code. Okay, yeah. In this case, at least per-hops reassembly is not as bad as it sounds. It's essentially, we thought that per-hop reassembly would be performing much worse than fragment forwarding, but it turned out to be a big surprise for us. Simulation tool. Now, one thing we wanted to do for sure was we wanted a realistic RF. So we used NS3 LRWPAN. So there is a Whitefield framework that we have developed a couple of years back, which we used for this experimentation. It uses NS3's LRWPAN in the backend for realistic RF. The advantage with this framework that we have is we can directly plug in the Contiki protocol stack on top of this framework, such that you can try out big networks and work out the whole scenario.
You have Thomas who's trying to ask a question.
Okay.
Yes. Yeah. Can you hear me? Good. This is working. So it's very cool that you're doing this these measurements with fragment forwarding. That's great. But
You speak a little bit louder or eat the mic, because we can hear you, but barely.
okay, let me reconnect. I'll reconnect.
So,
Yes,
what did
come
you
back.
say? Oh, he'll come back. All right. So yeah, this is the implementation. So we added the implementation at Slack reserves few extra bytes in the first fragment, because 6-flow compression is variable at every hop. So you have to make sure that you add some sort of slack in the first fragment. Slack is needed because the first fragment size might change en route. Second is the timers. There is a timer that has to be added. We used a 60-second timer to clear off entries, but then we try to check how many entries are getting cleared off because of the 60-second timers, and those are substantial. That means there are drops that are happening intermediately. Yeah, we clearly need more experiments to be done. Experiments with different RFs, ad hoc 802.11 with RTS-CTS. Maybe it might not work as well, but 802.11s uses L2 mesh, and this will result in a fragment forwarding like behavior. So already there are other techniques which are using the similar concept, like fragment forwarding. It will eventually lead to fragment forwarding at L2. So even the fragment forwarding should work better in that case. So we wanted to experiment with 802.11s in the next phase. More optimal pacing algorithms required. So should pacing be done only at the original receiver sender side? Well, that is very trivial to implement, but may not give you all the benefits. If you can do some sort of pacing at intermediate hops as well, it might be non-trivial to implement, but might give better gains. But we have not really experimented with any of these. Secondly, we want to check out the same experiment, check out the result with an hardware-based setup. We're trying to check whether we can do it on the hardware-based setup. Yeah, that's all. Is Thomas there?
No, he left and never hasn't joined back. So
Okay. Okay, that's all. Thanks to Yot for sharing his insight into his experiments. He presented data into IETF 102, which targeted primarily the memory utilization problem statement. And thanks to Castor and Pascal for design team mailing list discussions. Thank you.
he's just joined. Let's see if he's. on? Go ahead. Go ahead, Thomas.
Yes. Can you hear me better now? Okay. Is it better?
Let's try it. I think we can manage.
All right. So, it's very good that you do simulation, but I think anything that you're measuring has nothing to do with fragment forwarding. It is entirely due to the fact that you have bursty generation of data. The pacing, everything you talk about, it's a layer 2 thing. And throwing, throwing out conclusions like fragment forwarding is less efficient than per hop reassembly makes very little sense if you don't tune your MAC layer. I'm looking here at some studies that Yach did, where, I mean, we can send you this, where reliability is at 100%. So I will be very, very cautious in throwing out statements like this, given that it all depends on the MAC layer. And so maybe I'm misunderstanding, but my understanding is that what you're seeing is the effect of bursty traffic at nodes has nothing to do with the fragment forwarding itself.
So you mentioned two things, Thomas. So basically, you said that this is tied to layer 2 performance. Well, yes, it's tied to layer 2 performance. Second point you mentioned is the point that fragment forwarding enables this train of fragments to travel from one hop to another hop results in this situation. And 802.15.4 single channel mode of operation is still used, at least in our case. So this is why we wanted to experiment with that particular scenario.
Yeah, but what's the difference? Sorry, what's the difference between fragmenting a long packet versus sending many short application packets? This is the same thing, right? It has nothing to do with fragment forwarding.
Sorry, I didn't get you there. What did you say? Fragmenting?
He said sending a lot of small packets or sending a big packet that gets fragmented.
There's absolutely no difference. So what we try to check is whether blockwise transfer of CoAP will result in the same issue, because you are fragmenting at the application layer and then sending the packets. But then there is an acknowledgement at the application layer, and then you send the next packet in case of CoAP blockwise transfer. So it might not have this kind of issues. Fragment forwarding, there is
But that acknowledgement serves as a pacing, an automated pacing mechanism. What you're saying is that if you're using single channel 15.4, do not generate bursty traffic. That's all I'm reading from your results, right? Has nothing to do with fragment forwarding.
That's right.
All right. Thank you.
Thank you. Thank you.
Okay, thanks. Carlos, here you are.
Hello, everyone. My name is Carlos Gomez. I'm going to present the current status and a quick implementation report on the draft entitled IPv6 Mesh over Bluetooth Low Energy using IPSP. So first of all, let's take a look at the status of the document. So the last revision was -03. This was published in July before the last ITF. And in fact, the document has not been updated since the last ITF because we, the authors, believe that the document is ready in the sense that we are not aware of any outstanding issue or any potential updates that may need to be applied. However, we have been progressing on the side of implementing the draft. So we are happy to say that we have some running code and we have a first prototype implementation of the draft, which uses Bleach as a basis. So Bleach is an open source implementation of RFC 7668 for Contiki. And as you may recall, 7668 is the specification of IPv6 over BLE in star topology networks, which is actually the original network topology in BLE, whereby there's a single master, BLE master running as a 6LBR, which is connected directly to several BLE slaves, which are running as 6LNs. So in our implementation, we have extended Bleach in order to support the mesh draft. So among others, we have added the 6LR role and also now header compression is performed as per our mesh draft. Then one important detail in the implementation is that as of today, it is based on static routing. So recall that our mesh draft requires route over routing. However, no specific routing protocol is mandated. Then we have also been able to perform some initial experiments and tests using devices such as the ones you can see in the figure on the slide. These are CC2650 devices. The ones on the left are called Launchpad, the red ones. The other ones are called SenseAttack. All of them implement Bluetooth 4.1, and in our experiments, they all run Contiki OS. So, for example, we've been able to enable end-to-end communication in a topology like the one you can see here, which is a 3-hop BLE topology, between the 6LN on the left and the 6LBR on the right. Then we have also started to perform some preliminary latency measurements. And for example, we have measured an average RTT over a 2-hop scenario of 252 milliseconds when the BLE con-interval setting is 125 milliseconds. This parameter, con-interval, determines the time between 2 consecutive connection events in an established BLE link layer connection. Therefore, this means that the time between the moment when there's a packet to be sent and the actual time for transmission will be something between 0 and 125 milliseconds. Pascal.
Pascal Thubert, just to mention that the vendor of this particular chip, and I don't know if we can mention it, but that vendor has a Ripple implementation that's derived from Contiki. So I would really like, you're very close to having the dynamic protocol you're talking about, at least using Ripple. So if you try it, please let us know, because that would be great news. We'd love to see your work with Ripple over it. And the code exists for this chip.
Yeah, so I think that's actually the way to go, because we started with static routing as the initial step, let's say, but of course it would be better to have something like Ripple running here. Thank you. So yeah, based on this setting of con-interval, the expected average latency in a 1-hop, one-way transmission will be actually, in theory, 62.5 milliseconds. So the 2-hop RTT that we measured is actually matching quite well the theoretical expectation, since in this 2-hop round-trip time, we have 4 times this 1-hop, one-way delay. By the way, the application used to perform these measurements is a ping-like application which uses UDP packets. So, since at this moment, well, while we continue improving the implementation, since we are not aware of any outstanding issue in the document, we would like to ask if it would be a good moment to actually issue a working group last call.
Towards that end, so in your implementation, was there anything that surfaced because of it, or was it just you implemented everything, you didn't have to change the spec at all, or was there any lesson learned that you've been applied into the spec?
Not actually. So there was the last edition in -03, which didn't actually come up after implementing it or after trying, but was something that appeared in preparation for that. But other than that, we haven't found at this moment any issue after the implementation.
Okay, so the implementation validated what you have so far. That's really good news. Okay. Yeah, so I'll consult with my co-chair, who's not here right now, and we'll decide on this. But I mean, looks like you might be ready.
Yeah.
Good work.
Thank you.
Pascal.
Pascal again. I have a clarifying question here for the last call. Clearly, it makes a lot of sense to be able to run a routing protocol over it as opposed to static route. But I was wondering if you foresee any impact. Because basically, when you implement something, that's when you discover, oh, I did not think about adding this or that in my protocol. And here you're having running only with static routes. And I was just wondering, hey, would there be an impact if once we at least try it with Ripple, since it's there? So my intuition would be, hey, why don't we wait for this Ripple trial to make sure that we'll be able to have this dynamic protocol over it, or if you're really clear that there cannot be any change for making the dynamic protocol run. Intuitively, it's just setting routes, so it should be okay. But sometimes when you try it, I should have provided this information in here, and oh damn, So
Yeah, so in theory, I can't think of any potential issue because of running specifically REPL. Actually, we are providing support for a mesh topology, which is using some route over routing protocol. Well, we might have think further about that, or even try with implementation, or other ways. But at this moment, I don't foresee any potential issue in this regard. But anyway, I agree it's good to check.
Well, if you tell me that you run at least another dynamic protocol, I think I'm quite happy with that already, right? But having only static route feels I feel like, maybe we're missing something about the two-way exchanges or whatever happens, or the broadcast domains or anything which could actually be a prime for routing. So I just would have liked you to run a routing. And I mentioned REPL because I know it's available on Contiki or derived Contiki on this platform. So I said, hey, let's try it before we ship this thing. Make sure it works.
Okay.
Lijo Thomas, great work. I just want to add one thing is, does your implementation in the Contiki is shared in the open source, or?
No, not at the moment, because actually this is quite recent,
Okay.
with some results just from almost last week.
Okay.
But yeah, the plan would be to, once this is more stable, to open it and share this. Actually, the implementation is based on Bleach, which is an open source implementation.
Yes.
And the plan is to actually offer this also as an open source
Yeah, it
implementation.
will be great. Yes. Thank you.
Thank you.
Okay, so yeah, let's keep chatting. Thank you.
Thank you.
So that's all we had planned for today. Before we call it a day, does anybody have the blue sheets? There should be two lying around somewhere. Could you bring them up to the front of the room? And if anybody has anything else, announcements or whatever, this is the time. Otherwise, we can call it a day. Seeing nothing, I guess we're adjourned. So enjoy the rest of the time. Thanks, folks. Excellent. That is good. Thank you very much. I appreciate that. Not necessarily. Well, I don't. Oh, I'm right here now, but I'm just so, yeah. Samita also, right? Did you see there was a Suresh announced it? Yeah, so both of us are. It's been a few years, so I think it's time to get new. Yeah, it's probably a good thing by design.
Can I on the if path, because I don't see the save provision button, so if you can just check that everything actually is.
I haven't even looked at the Etherpad. Let's see. This is typically here. No, not that one. This is the easy one. This, no, this one, right? Meeting notes. No, this is Etherpad 103.